Hello and welcome to this lecture 6 of module 3 on random variable. In this lecture we will cover the probability distribution of continuous random variable. In the last lecture we covered the discrete random variables. Similarly, for some continuous random variable there are some standard probability distribution functions are there, which are very widely used in different problems in civil engineering. We will see those distributions. Maybe in today's class as well as next class we will continue the discussion through different probability distributions for continuous random variables. So, at the starting we will quickly recapitulate the PDF, that is probability density function. You know that for the discrete random variable what we refer is the probability density function. So, the probability density function and the requirement for the to be a valid PDF for the continuous random variable, we will see that very quickly, as this was we discussed in the earlier lectures as well, and after that we will go through the different distribution function. To list it, we will start with the uniform distribution. Then we will see the normal distribution, log normal distribution, exponential distribution, gamma distribution, Weibull distribution and beta distribution. The list of this distribution may not be exhaustive, but these are the distribution which are generally and widely used for different problems in civil engineering. So, we will cover them one after another and we will just show there for which type of problems which distributions will be most suitable, and that is generally decided based on their shape. For example, when we talk about the uniform distribution, this is generally bounded from the lower side as well as the upper side, and in between that the density is uniform. Similarly, the normal distribution is the support of normal distribution is spanning from the minus infinity to plus infinity. So, which is the entire range of the real axis. And log normal distribution, exponential distribution and gamma distribution generally are lower bounded, having some lower bound, and this bound is generally at the origin, that is 0. And then we will see the Weibull distribution, beta distribution. This beta distribution again is the bounded distribution, and we will see their different possible application of this one in different civil engineering problem. In this lecture and as well as in the next lecture, that is in this module, what we will discuss is their basic properties of this distribution and what are their characteristics. Application of this any specific distribution to some specific problem of civil engineering will be discussed in the subsequent modules. Most probably it is in module 5. So, we will start with this very brief recapitulation of probability density function for the continuous random variable. So, as we discussed in the earlier classes, earlier lectures, that a continuous random variable is a function that can take any value in the sense of the continuous range within the given range of that random variable. The continuous random variable possesses a continuous probability density function. So, this continuous probability density function, we know that over the range of this possible range of this random variable, over that range this function is continuous, and obviously some properties should be satisfied by this function to be a valid PDF. Now, probability of such random variables identifies the probability of a value of the random variable falling within a particular interval. So, this is basically the difference between the discrete and the continuous random variable. Here, as we are talking the function as a density function. So, at a particular point, at a particular value of this random variable, if we see the PDF, then what is giving is the density. Now, when we are talking about a small interval or small range of this one, then that area below that PDF is the probability. So, that's why the probability, what it identifies is the probability of that random variable falling within that particular interval. So, one small interval is needed to define what is the probability for that random variable falling within that particular interval. then these are the properties that should be followed to be a valid PDF. That is, a probability density function PDF is conventionally as we have seen earlier, that is, it is denoted by fxx, where this is the capital X which is denoting that random variable, and this is a small x which is denoting that dummy variable or the particular value of that random variable. So there are two properties that it should follow. We know that at any for all values of all feasible values of this x, this value of this function should be greater than equal to 0, and it should integrate to unity to satisfy the second axiom, that total probability within the all possible range, or that feasible over the feasible range of this random variable, which is known as the support of the random variable. Over this support, it should be equal to 1. So with this, now we will see, we will go through different probability distribution function, and first we will start with the uniform distribution. So any random variable x is uniformly distributed random variable if its probability density function is given by this equation, that is fx, this will be capital X, fx with this variable x and this alpha, beta, or any such thing which is shown here are generally the parameter of that distribution. So here the parameters are alpha and beta. So with this parameter, this distribution is expressed by 1 by beta minus alpha for the range when this x lies between alpha and beta, that is, the lower limit is alpha and upper limit is beta. Outside this range, anywhere the value of this function is equals to 0. Now if we see this function, then before we call that this is a probability density function, we have to see that whether those two properties are followed or not. So we see that as this beta is greater than alpha, so this quantity is greater than 0 always, and in the outside this region this is equal to 0. So the first property, that is, it should be greater than equal to 0, is satisfied, and obviously this 1 by beta minus alpha, if we now integrate it over this alpha to beta, so this range from this beta to alpha, which is again this beta minus alpha, this will be equal to 1. So this is the complete form of this uniformly distributed uniform distribution. And we know that if we say that the cumulative distribution function will be given by this x minus alpha divided by beta minus alpha. Here the diagram or the how this distribution looks like is shown here. This is your alpha limit and this is your beta limit. Now if we just see it once here, that now this is what we are calling as this alpha and this what we are calling as beta, and now this side is your that value of that function fx, and this is your the x. So here the possible range is between alpha and beta, and this is a closed boundary. Closed boundary means that less than equal to sign is shown. So this is the closed boundary, that means it is inclusive of these two values. So at this value the probability is 1 by, from this point to this point, this probability, if I just show as a indicative line, is 1 by beta minus alpha. So from this range to this range the density is uniform all over this region. That's why the name is uniform distribution, and just for this reference we are just noting these two lines from this alpha to beta. Now when we are talking about what is its cumulative distribution, that means any value within this range up to the x, we have to calculate what is the total area up to that point, as we have seen in the earlier description as well for the CDF. So at this point I have to point that what is the value for that region in this. So, this point when you are talking about this cumulative distribution function, this point implies that the total area covered up to that point. So, obviously, the total area covered at alpha is nothing, 0. So, this source corresponds to this point, and when it is in this way, if we just move this x up to this beta, obviously from this second property it should touch the values at total area will be equals to 1. So, this value should come as 1, and as this is uniform, this should be a straight line starting from 0 at alpha and 1 at beta. So, this will be your CDF, that is cumulative distribution function for uniform distribution. So, which is here shown here, you can see from this that cumulative distribution function, that is x minus alpha by beta minus alpha. Now, if you put that x is equals to alpha here, then you are getting it here to be 0, and if you put that x equals to beta, then you are getting this value as to be your 1. So, which is shown in this diagram as well. So, this is that density, that is that density function. Now, the some different initial parameters that we have discussed in the earlier lectures, that is mean, variance and coefficients. If we calculate these things for the uniform distribution, it comes as this. There is a mean is given by mu equals to alpha plus beta by 2, which is obvious from this diagram as well. So, that mean value of this one, as this distribution is uniform. So, mean value should be equal to should be at the midpoint of these two range. So, that midpoint is nothing but your alpha plus beta by 2. Now, before coming to this variance, if I see the coefficient of skewness, then coefficient of skewness, if we see, then we know that it is the measure of the symmetry with respect to the its mean. So, we see that this is also a symmetric with respect to the mean, that is why the skewness also will be 0. So, this is, so mean is given by this average value of this lower and upper bound of that distribution, and the coefficient of skewness is 0 as the distribution is symmetric about the mean. And variance also, the equation that we use, that it should be from the mean, and if we take the square and then we multiply it with that probability density function and integrate over the entire support, then we get that the variance should equals to beta minus alpha whole square divided by 12. So, this is your variance, and obviously skewness is 0 as discussed. Now, any specific civil engineering application, sometimes if we see, then if we take the example of a structural member which is made up of a material which is a uniform characteristics all over, and it is subject to a particular loading condition, then that structural member can fail. Failing means it can break or rupture at a distance x from the one end. Now, the distribution of that x can be assumed to be uniform with the support 0 to L. Now, if this one, so this is the structural member. Now, the location of the failure from the one end of that member, that if we take that particular distance from one end is the random variable, then it can happen anywhere. So, the probability that the distribution of the probability for this random variable capital X can be assumed to be uniform, and this is equals to 1 by L. So, and this is valid from the 0 to the entire length of this structural member. So, that is why this is 1 by L and it is 0 elsewhere. Now, if we draw its PDF, it looks like this, that is from 0 to L, it is uniformly distributed, which is equals to 1 by L. Considering the fact that the total area below this curve, below this PDF should be equals to 1. Now, this analogy, this example can be analogously can be extended to the other examples like that road accident on a highway stretch identified to be the accident prone. Now, if the total length of this road is equals to 0, so that location of this accident can happen any point over this stretch. So, that is also can be followed as a uniform distribution. Now, we will to start with, we started that a uniform distribution, which is easy in the sense from this mathematical concept, and we will proceed now to the normal or the Gaussian distribution. And this normal and Gaussian distribution is one of the most important distribution in every field, including civil engineering, and many applications has found to be is very useful. This normal distribution is useful for many applications in different research field. So, so that is why this normal or the Gaussian distribution is most popular distribution among the among all continuous probability distribution, and this is a continuous probability distribution with unbounded support. Unbounded support means mathematically it can take the values from -infinity to +infinity, and it is symmetrical distribution about the mean. So, these two properties are there, and this is a two parameter distribution again, that is the mean is mu and variance is sigma square. For the uniform distribution also we have shown that there are two parameters alpha and beta, which are basically the bound for the distribution. Here also there are two distribution, one is this mu and another one is the sigma square. We will see how the distribution looks like and its different properties in the success in this, that this is the PDF for this normal distribution. So, PDF of the random variable x having normal or Gaussian distribution with the parameter mu and other parameter is sigma square, it is expressed as that fx x with these two parameter is equals to 1 by square root of 2 pi sigma. Remember that this sigma is outside this square root. If it is within, obviously one square will come here, multiplied by exponential of -12 x minus mu by sigma whole square, and this support for this x is from -infinity to +infinity as just now discussed. So, this PDF results in a bell-shaped curve, and which is symmetric about the mean. In the earlier cases also, if you see that this distribution generally looks like this. So, this distribution generally looks like this. So, this is having its mean, and obviously the mean, mode and median are same here, and this is with respect to this. This is known as a bell-shaped curve, and this is symmetric with respect to this mean. And if we see again, if we see its cumulative density function, then obviously we can say that it starts from this -infinity and goes up to this +infinity. So, if we take that any particular point here and total area, if we calculate and put it some value here, then this CDF, that is this is your PDF, and this is your CDF, and this generally goes and become again it touch this 1 at infinity +infinity, it is asymptotic to this line 1, and this is asymptotic to the line 0 at -infinity. So, this is the how this cumulative distribution looks like, and this is how the PDF looks like for one normal or Gaussian distribution. So, mathematically we know that to get that cumulative distribution function, we have to integrate from this left hand support, that is -infinity to it can go up to x, and this integration from this -infinity to x of this PDF, this integration of this one from this, it will give you the CDF. Now this integration is difficult, and we will see that how this is overcome through this numerical integration and with the available chart that we will discuss in a minute. Before that, we will show this example of this bell shaped curve that we have shown is this bell shaped curve. The parameter for this curve is that mu is equals to 1 and sigma is equals to 1.2. So as this parameter mu is equals to 1, you can see that it is the maximum density is at this point 1. So this mu is basically the location parameter where the maximum density is located. So that is signified by this mu, and sigma also it is generally showing the spread over this mean, and we will show this one in the examples how these things can affect the shape of this curve. And this is your for the same PDF with mu equals to 1 and sigma equals to 2. If we calculate what should be the cumulative distribution function, that is CDF, then it looks like this. And this line, you can see that this is asymptotic to 1 at plus infinity, and this one towards the left, it is asymptotic to 0 towards minus infinity. Now these parameters of this normal distribution, as we discussed that this normal distribution is a 2-parameter distribution. So the first parameter is your mean. It is the shape parameter. It is a shape parameter of this normal distribution, and it is generally denoted by this mu. And the second parameter is the variance. This is the scale parameter of the normal distribution, and this is generally denoted by sigma square. Now the coefficient of skewness is again 0, similar to the uniform distribution what we discussed earlier. This is 0 because this distribution is also symmetric about the mean. That's why this skewness is 0. Now if we see the effect of change of this parameter, as we were talking, that effect of change in this parameter value on this normal PDF, then it looks like this. We have plotted here 3 different normal distribution, the PDF for the normal distribution with different parameters. The blue line, that is the middle one, if you see, this is for the sigma value 1.5. For all these 3 distribution that is shown here having the same mean, mu equals to 0. So that's why for all this distribution you can see that maximum density is concentrated at x equals to 0. Now this blue curve, this blue one is having the sigma value equals to 1.5, whereas this green one is having the sigma value is 0.75, and this black one is having the sigma value is equals to 1. Now you see for this black one, the sigma value is the is 1.5, which is the maximum, here. So that is why, keeping the mean same for all 3 distribution, this is more spread, the spread is more about its mean, and so it is reflected from its value of this parameter sigma, which is 1.5. Similarly for this green one, the sigma value is the minimum, and which is 0.75. That is why it is the spread about the mean is the minimum most among these 3 distribution curve. So this sigma generally controls the spread about the mean, which is reflected from this diagram. Now the effect of change in the parameter value, the second parameter now we are taking, this is that mu. Now in these 3 plot, again what we have kept same is that sigma. Now for all these 3 curves, sigma is equals to 1.5. Now, so as this sigma is same, then you can see that the spread about their mean, the respective mean is same for all three curves. Now, as we have changed, for this blue one mu is -2, for the black one mu is 0, and for green one mu is 2. So, you can see that this is generally shifted from the one location to another location. For blue one it is centered at -2, for black one it is at 0, and for green one it is at 2. So, where this it is centered, so that is controlled by this parameter mu. And now, if we take some standard example of this normal distribution in civil engineering, if a number of concrete cubes, so one example is that strength of this concrete, if a number of concrete cube prepared through the identical methods and cured under the identical circumstances are tested for their crushing strength, it is observed that their crushing strength is a normally distributed random variable. Now, the crushing strength that is available in at least 95% of the sample is called the characteristic strength or the 95% dependable strength. You know that example of the characteristic strength in the civil for the strength of the concrete is that it is that in the 95% cases if we see that the particular strength of the cube is exceeded, that is generally denoted by this crushing strength. Now, that how we can say that this is the 95% cases it is exceeded. So, it is generally found to follow a normal distribution keeping its mean, and we consider that strength where it should be exceeded at the 95% cases to designate that particular strength to be the characteristic strength of that concrete of that particular concrete. So, this is how we define that characteristic strength of the concrete cube. Now, there are some nice properties of this normally distributed random variable, which is known as this additive property. If a random variable x is normally distributed with its parameter mu and sigma, we discussed that normal distribution having two parameters mu and sigma, then if we get another random variable that which is related to this earlier one, that is x, through this equation, that is y is equals to a plus bx, that is the random variable is multiplied by b and added with a, then this y is also this y will also be normally distributed. However, its parameters will change like this, that it's the first parameter in place of this mu it will be a plus b mu, and its second parameter which is sigma square is equals to b square sigma square. So, while getting these new parameters, what we are doing is that we are just putting the mean value, that is that first parameter value here, and getting the mean for this for this new random variable. And when we are talking about the variance, that is the spread around the mean, then the constant term that we are adding, that is not affecting, but what is affecting is by its multiplying coefficient, and it should be squared. So, that is b square multiplied by this sigma square. Similarly, if there are n numbers of such normally distributed random variable, and if we can say that these are independent to each other, then if we create another new random variable which is y is equals to a plus b1 multiplied by x1, b2 multiplied by x2, similarly up to bn multiplied by xn, then this y will also be a normally distributed and its parameter will be, so we will just put the individual mean of these random variables to get the mean for this y, which is, so the mu y is equals to a plus summation of bi mu I. So, a plus b1 mu 1 plus b2 mu 2 etc. up to bn mu n, and for this sigma square it should be the coefficient for those random variable that square times their individual variance, and their summation up should give you this 1. The second property generally leading to the central limit theorem, and that we will discuss in the subsequent lectures. We will see that we can relax the requirement of this normal distribution for this random variable if these are simply, if they are independent and identically distributed itself. We can say that this y will have this normal distribution, which is the result of the central limit theorem will be discussed later. And the first property when we are talking about, that is the y is equals to a plus bx, this y can be treated as a function of x, which is the which will be discussed in greater detail in the next module, where we will discuss about that functions of random variable. So while discussing the functions of random variable, we will know, if we know the properties, that parameters for one one random variable, how to get the parameters for the or the distribution as well as parameters as well as distribution for its function. So this normal distribution is one example that we have shown here. In while discussing the functions of random variable, this will be discussed in a general way, irrespective of this of any particular distribution of the original random variable. Now another distribution which is the which is derived from this normal distribution is known as the standard normal distribution. This standard normal distribution, when a normal distribution is having its mean mu equals to 0 and variance sigma square equals to 1, then this particular normal distribution with the specific values of these parameters is known as the standard normal distribution. So in this original distributional form, that is what we have shown it earlier, that this distribution, if we just put mu equals to 0 and sigma equals to 1, what the distribution form we will get, that will be the standard normal distribution. Instead of using x there, we are using z as the dummy variable. So this is your standard normal distribution. To continue with our same notation, this is also, as this is also continuous, instead of p, this will be f, and this is the capital Z and this is the small z. So this is specific value and this is the random variable. So whose distribution is 1 by square root 2 pi exponential minus z square by 2, and obviously the z is having the support from minus infinity to plus infinity. So this is also normal distribution which is having the mean mu and variance 1. The cumulative distribution for this standard normal distribution again can be found out from integrating it from this left support to the specific value z, which is 1 by square root 2 pi exponential minus z square by 2. So integrating from this left support to the particular value x, and this is also will be the capital F and this z less than equals to a particular value z, which is giving you the cumulative probability distribution. Now we should know what is the use of this distribution. The use of this distribution and why we need this specific distribution with this specific parameter is that this integration, whenever we are talking about this integration, which is important to calculate the probability, it is not this integration cannot be done in the closed form. So we have to go for some numerical integration, and the numerically integrated values are available for the standard normal distribution. Now for any general normal distribution, we can convert it first to the standard normal distribution and get its desired probability, and that we will discuss in a minute. So before that, this is how this distribution, that is PDF, probability density function, looks like, and as you know that its mean is equals to 0 and sigma is equals to 1. So that's why it is centered at 0. Basically its support is again that from minus infinity to plus infinity. But one thing you can see that most of the probabilities is concentrated between minus 3 to plus 3. Now, why the thing that we are discussing, why we need this standard normal distribution is as follows. If a random variable x is normally distributed with mean mu and the variance sigma square, then the probability of x being less than or equal to x is given by this particular distribution. Now, as the above integration cannot be evaluated analytically, as we discussed just now, the numerically computed values are tabulated taking this mu equals to 0 and sigma equals to 1, that is the standard normal distribution. So, for the standard normal distribution, these values are numerically computed and listed. Now, for all other normal distribution with any values of these parameters, that is, if this mu is not equal to 0 and this sigma square is not equal to 1, then the cumulative probabilities can be determined by converting this x to its reduced variate. So, how it is converted? That is, this x, that particular random variable, is deducted from its mean, that is the whatever the value mean is there, and it is divided by sigma. So, we get a new random variable which is z. Now, we have seen just now in a minute, we have seen that if that y is equals to a plus b x just few earlier, if this is normal distribution, we have seen that its mean, the mean of this y is a plus b mu and its variance is b square sigma square. Now, what we are doing here, the conversion is just z is equals to x minus mu by sigma. If I just write in that form, that is mu by sigma plus 1 by sigma x. So, here your a is equals to minus mu by sigma and your b is equals to 1 by sigma. So, that the mean for this z will be a plus b mu. If I take it from here, a plus b mu, and if I put this value, is equals to minus mu by sigma plus this 1 by this b is 1 by sigma multiplied by mu, which is 0, and for this variance for this z is b square sigma square, which is again this b square is 1 by sigma square multiplied by sigma square equals to 1. So, we have converted it in such a way that the mean for this new random variable is 0 and variance for this new random variable becomes 1. So, through this conversion of any normally distributed random variable, we can generate another new random variable which is again normal distribution with mean 0 and standard deviation 1, and this conversion is irrespective of any specific value of mu and sigma that original random variable is having. So, once we can convert this one, then we can use this standard normal distribution chart, which is generally looks like this. So, this is your that PDF of this normal distribution, and these cumulative values are listed as follows. That is, for any specific value of this z, this is basically started from minus 5 and goes like this and coming and going up to 5, and we know that from this effectively from minus 3 to plus 3 itself, most of the probabilities are exhausted. So, if I just zoom it here, then you can see for the value when this z value is at 0, that is at the mean, and we know that the total probability covered due to the property of its symmetry should be equals to 0.5, which is shown here. Now, as we are for in any value, suppose that if I take that 0.21, so this is your 0.2 and this is the second decimal point 0.21. So, up to point z equals to up to 0.21, the probability covered is 0.5832. Now we will see one example how to calculate the probability for any normal distribution that we will see. So this is how we have to read this standard normal distribution, and these tables are generally available in any standard textbook. So what we have found from this distribution is that from the standard normal distribution curve, it can be observed that this 99.74% of the area under the curve falls inside the region bounded by plus minus 3 sigma. So for the standard normal distribution, what we saw that sigma equals to 1. So from this minus 3 to plus 3, so this much probability, which is almost close to 1, is already covered in that. This is particularly important in the real life scenario where a random variable may be bounded by x equals to 0, but can still considered to be normally distributed if mu is greater than 3 sigma. So in the real life, sometimes we can come across to the situation that those random variables are effectively lower bounded by 0, but if we see that its mean is mean is away from the origin with a magnitude of 3 sigma, then we can once see that whether that can also be considered to be a normal distribution, as we know that below this 0 means left side of this 0, so towards a negative value, effectively the probability is 0. Now, if we just want to do one small exercise how to calculate the probability using this standard normal distribution, let us consider a random variable x that is normally distributed, and once we say that this is normally distributed, we have to specify its parameter. So with mean equals to 4.35 and sigma is equals to 0.59. So now if we look for the probability that this random variable will take a value between 4 and 5, then this can be calculated from this cumulative standard normal probability table. How? So our intention to get the probability of x lying between 5 to 4 should be equals to first what we are doing is that we are converting these two limits, that is the 5 and 4, this we are converting to a reduced variate. So how to convert it to the reduced variate? That particular value minus its mean divided by sigma. So so if we reduce it, the upper limit corresponding reduced variate, lower limit corresponding reduced variate. So this is again 4 minus mean divided by sigma. Now this value ends up to the 1.1 and this is minus 0.59. Now this one, as these are reduced variate, so this is having the mean is equals to 0 and variance is equals to 1. So this we can read from this standard normal distribution for 1.1. So if we refer to this chart, then we can see that where this 1.1, so this cell, if you can read it, that is 0.4838. So what is meant is that starting from here up to 1.1, total area covered is 0.8438. So this is 8643, maybe this will be 84. So this might be a mistake, that is this might be that 84. So this is how we read this probability for a particular value of the standard normal distribution, and similarly we can read this value for the other limit, and we can deduct this probability to get this value. So what is actually here is done graphically is like this. So first of all, this is reduced, this is a reduced variate. So if this is your 0, then the reduced variate is looks like this. Now from the 1.1, what is the value we get from this table is the total area from this, from the left support to that point 1.1. So this total area, that is the total probability we will get from that standard normal distribution table, and for the left one is the minus 0.59, maybe somewhere here minus 0.59. So, what we are doing that up to this much, what is this area that we are deducting, so that we will get what is there in this area only. So, what is the total area between these two limit we will get. So, the total area up to this one minus total area up to this point to calculate the probability between these two limits. So, this is exactly is done here. First of all, we have converted to the reduced variate, which is 1.1, another one is this minus 0.59, this 5 corresponds to 1.1 and this 4 corresponds to 0.59, and these two values are taken from this standard normal distribution table. So, here this graphical representation is shown here again, that is 1.1 this area. So, up to this, that value which is indicating is the total area from this minus infinity to this point. So, that is why we have to get only this much area, we have to deduct the area which is up to that point of minus 0.59. So, this area should be deducted to get the area in between these two limits. Next distribution that we are going to discuss is the log normal distribution. This is also known as the Galton distribution. Any random variable x is a log normal random variable if its probability density function is given by as follows. Again, it is having two parameters, one is mu and this sigma square, which is 1 by x sigma square root 2 pi exponential minus 1 by 2 in bracket log natural x minus mu divided by sigma whole square, and its limit for the x is from so this limit is this is a mistake, this limit from the 0 to infinity. So, why this is important and what is the difference between this normal distribution is that for the normal distribution it varies from minus infinity to plus infinity, but this log normal distribution support is from 0 to infinity. Basically, what we are doing again is that we are just taking that one random variable, we are taking its log and it is related through this equation, that is y is equals to log x. And now, what is shown here is that if this random variable x is log normally distributed, then that y, if I take that log x is the normally distributed. So, if we come across with any distribution which is log normally distributed, we can take its log and convert it to the normal distribution, and again we can use the same procedure which is followed for the normal distribution. Now, so as it is related to this, as the log normal distribution is related to the normal distribution through this functional transformation, this will again be clear in the next module where we are discussing about the function of random variable. So, if this distribution is known or if this normal distribution is known, what is the distribution for this x, and through that one it can be easily shown that this distribution of this x is following is having the form like this. This will be 0, this is not minus infinity, this is 0. And again the cumulative distribution function is given by this one, where this is your that cumulative distribution of this normal distribution, and ln x minus mu by sigma. Basically, if you see this mu and sigma, that is the parameter of this log normal distribution, this mu is the mean of the variable x after taking its log. So, after taking the log of x, if we calculate the mean, then that is equals to its parameters mu, and similarly if we take the variance, this is this sigma square. Now, this is how a log normal distribution with this log mu is equals to 1 and log sigma equals to 0.12 looks like. So, this is lower bounded by 0 and go up to plus infinity, that which is the support for this log normal distribution. And Similarly, this is your cumulative distribution function for the log normal distribution. Now, this mean of this log normal distribution is expectation of this x, which can be shown that e power mu plus 1 by sigma square, that is, this is the mean for that variable x, and this mu, this is the mean after taking the log of this of the distribution of x. If we calculate the mean, this is that mean which was discussed. Again, the variance of this distribution, that is variance of x, is equals to mu x. Now, this subscript x is shown as, this is for this mu for this x. So, this one, that square multiplied by exponential sigma square minus 1. Coefficient of variance is again given by the CV of this x, that is the random variable x, is equals to square root of e power sigma square minus 1, and coefficient of skewness is given by, for this gamma x, is equals to 3 multiplied by CV x plus CV x square, that CV x cube. The distribution is positively skewed, and with decrease of the coefficient of variation, the skewness also decreases, which can be reflected from this equation. Now, for a log normally distributed random variable x, the sample statistics for y equals to log x, that is, we have some observations, some sample data, we have taken its log. If we take that log, then how we can get the mean of that converted random variable. This is obtained through this equation, that is y bar after taking the log, its mean is equals to half ln x bar square divided by 1 plus CV x square. So, this CV is the coefficient of variance for that observation x, and this x bar is the mean for that particular observation of the observed values, which is square. The sample variance for the y equals to log x, again this one is equals to sy square is equals to ln 1 plus CV x. So, this is the coefficient of variation whose square plus 1, take the log, get that sample variance of y. This coefficient of variation, as we know, is the ratio of this standard deviation of the x divided by mean of that x. Now, in civil engineering, the distribution of annual river flow data may follow the log normal distribution. The stream flow values generally are greater than 0, that is, its lower bound is 0, and the probability density for extremely low stream flows are quite less. This is obviously for some kind of big rivers, and if we see that it is generally having some contribution from this ground flow or the snow fed rivers like that. So, generally some flow is maintained some flow is maintained throughout the year. So, the the probability is low for the extremely low flows. Then the probability densities are increases with the increasing amount of this annual flow for the moderate values of the stream flow, and again it decreases progressively for the increasing stream flow. So, the probability for the extremely high stream flow again is very less. So, what we can see is that it starts from 0, take the peak, and again it is coming down, so far as the density of the probability is concerned over the range of this annual river flow. So, this can follow, we cannot confirm it, and we cannot say it as a general case that all the annual rivers are always follow the log normal distribution, that even though we cannot say that, but there is a possibility that this may follow a log normal distribution. Next we will discuss that exponential distribution. It is the probability distribution that describes the time between the events in an experiment where the outcomes occur continuously and independently at a constant average rate. It is generally used as a decay function in the engineering problems. So, this distribution is mathematically very effective to show, and in the previous lectures also we have taken this example to show its different properties of the continuous random variable, and we know that its probability density function looks like the lambda e power minus lambda x, for this x greater than equal to 0 and elsewhere it is 0. And here it is a single parameter distribution and the parameter is lambda. And if we take, we in the earlier lectures also we have seen that this cumulative distribution function can be shown as the 1 minus e power minus lambda x, and its distribution, this PDF, that is probability density function with a particular value of lambda equals to 1 taken here is looks like this, and its cumulative distribution again looks like this, which is starting from 0 and going asymptotic to 1 at x equals to infinity. And these things also we calculated earlier. Its mean is given by expectation of x is given by 1 by lambda and variance is 1 by sigma square. Its skewness can be shown is equals to 2, and coefficient of variance also we shown it earlier, and which is equals to 1. In the earlier lecture we covered this distribution as example. So, if we take that daily rainfall depth and the probability density is highest for this 0 rainfall, we know that most of the days, if in case the most of the days are dry days, then it is the maximum probability is concentrated as 0. The probability density becomes progressively lesser for the higher values of the rainfall depth, and it is very less for the extremely high rainfall depths. Thus, this may follow, again it should now may word should be followed. So, daily rainfall depth may follow an exponential distribution, and with this we stop with this exponential distribution here. So, in this lecture we covered that uniform distribution, normal distribution, log normal distribution and exponential distribution. There are some more distributions are also important, and that we will cover in the next class. And then we will go through the next module, and in successive modules application of this kind of distribution in differential problem for different models will be explained later. Thank you.